Hello, I'm Daryl Harriman from the Electronics 71 Digital Electronics class, and I'm going to take you through a circuit design using Logisim. But first we have a truth table, and on the truth table we have all of the 4-bit input combinations. So with 4 bits, 2 to the 4th power is 16, which means we have 16 combinations that go from 0 to 15. So I selected some ones on the output column here, and then for each of those ones, those would be true outputs on our circuit when we have those inputs. So for example, if all 4 inputs A, B, C, and D are 0, the output should be a 1. And this is the term that would represent a 0 in a Boolean expression. So a 0 would be a not A, not B, not C, and not D. Then also likewise for a 2 on the input, which is a 0010 in binary, which is a not A, not B, a C, and not D. So we have 7 different terms, and all of those terms are, each of the variables in those terms are ANDed together, and then each ANDed term is ORed with the next term, and then ORed with the next term up until they're all ORed together. Then in the end, we should have an output that outputs a true when the input is either a 0, a 2, an 8, a 10, 11, or a 14 or 15. So any of those inputs, the output on our circuit should be true. So what I'm going to do is take that expression, which I have the expression already entered on a Logisim document, and on this program, I have the template file loaded, so I've got my basic logic gates at the top of the program here. And then we have other gates here under gates. If we need to, we could use those. And then
It's
we've
1 o'clock.
got an input. So I've got an A. Command D will duplicate. So I'm going to make a B input. So I change my label to a B. Then I'm going to duplicate this so I can have a C and D. So I select both of them, Command D. It gives me 2 more. And I need to change the labels to C and D. So I'm not going to go through the entire circuit because that'll take a while, but I'll show you enough to get started. And then I'll show you what the finished circuit looks like when we're done. So we have A, B, C, and D input, and those are up here on the top left corner, the input pins. And so each of these has 3 AND gates. Each term has 3 AND gates. So we're going to need, for this unsimplified expression, we're going to need 3 AND gates for each term, and there's 7 terms, so that's going to be 21 AND gates we need. And then we're going to need 6 OR gates, 3, 4, 5, 6 OR gates to OR those terms together. So again, this is unsimplified. So what I'm going to do is take and Command D. I'm going to basically set this up so I can duplicate it 6 more times. And so I'm going to even connect here and here. And it's red right now because I have no inputs on my gate, but that's okay. I'm going to line this up with my top. And now we also have not variables. So we're going to need a not for A, B, C, and D. So a inverter. So what I'm going to do is make enough room so I can bring down all 4 lines on my A, B, C, and D to go to my other gates. So I'm going to need 4 of those. We may have to make some adjustments, but to start with, we'll go with this. And okay, so I said I was going to do 7 groups of these. So I select all 3, a Command D. That gives me 2 groups. And I'm going to move it down far enough so I can put my signal through here, a wire through there. And then I'm going to select those 6, Command D. So I'm going to move that one down here, about there. And now I need, so there's 4 groups. I need 7 groups total. So I'm going to select 3, do a Command D, and move those down here. Okay, now we have 7 groups. So the first term is a not A, not B, not C, and not D. So I could take my input pins and connect them to my inverters. And then the first term was a not A, so we'll hook a not A here. I'm going to have to probably make a little more room for another wire for my not terms to come down to my other inputs. And so we have a not B, so I'm going to take this one and move it over 2 clicks. And then a not C, so I'm going to take this one and move it to here, come to this gate. Then a not D, so I'm going to come to here and to this gate. So here is a not A, not B, not C, and not D. And they're all 0 right now, so the not on all of those is 1s on all. So this is an output of 1, which means we have a 0 input. The next one is for a 2, a not A, not B, C, and not D. Now, I left a little room here, so I think we can do this. I'm going to take my not A here. My not B is here. My C, I'm going to start from here and go to my C. And, whoops, that's to the not C. Got to be careful. Okay, I want to come over here to C. And a not D. So this is going to be my not D here. So this is my second term. So you can see how this is working out. We'll do one more. So A, not B, not C, not D. So this is a 8 in decimal. It's a 1, 0, 0, 0. So A is a 1, right? And I'm going to come over to here. I'll show you what's happening here in a second. So I'm going to have a 1 that comes down here to wherever I need it. Now B I'm going to have come down to wherever I need it. And I'll probably have some extra wire there, but we'll delete that afterwards. So I'm going to take my C, and then this is my D. And I do the same thing on my not terms. I'm going to bring my A down. My B is here. My C is here. So I've got them in order, A, B, C, and D, and then not A, not B, not C, and not D. And that makes it easy to keep track of where you're connecting your gates to. So this, I don't always do it by this design, but when you have a lot of sub-circuits or little sections, it makes it easier. All right, so we've got a second term here. Our third term was A and not B, not C, and not D. So A is way over here, which we have connected already, is this wire here. Now the not B, so that's going to be my second wire on my not terms. That's my not B. Then not C is the third wire. And we ran into a little issue here. Okay, I'll go to here, not C, and then not D. So we're going to have the same issue here. I'm going to run into, okay, so that's my third term. Now the next term is a 1, 0, 1, 0. So that's a 10 decimal, right? So 1, 0, 1, 0 is a A. So I'll come over here to A. A 0, which is a not B. A 1, which is a C. And a 0, which is a not D. See how quick and easy that was? Whoops. So we got a 1, 0, 1, 0. And that gives us our fourth term. So we're going to hook up all of these the same way. And I'm going to just show you how we're going to do. We're going to take each of these and run them into OR gates. And it doesn't matter which order you put them into OR gates. I could do the top two first, I could do the middle two first, it doesn't matter, because the OR operation is commutative. So I can reverse the order without changing the output. So I can do it like this, and then I could OR these two together. And as long as I end up having all these outputs from all these gates ORed together, when I'm done, I should have a good value. So what I'm going to do now is I've got this circuit completed already. Rather than taking you through all of that, I'm going to show you the completed circuit here. So I've got this circuit on the left here completed. That's basically what I was working on there. I also put tunnels here so that I could build equivalent circuits on the right here. And using the tunnels, I can take my values from my input pins and output them over here on the right to go to my logic circuits. So this unsimplified circuit on the left performs exactly the same as these three simplified circuits on the right. So we're going to get into how to simplify these expressions using about three different methods. One is a Karnaugh mapping, one is called a Quine-McCluskey algorithm, and another one is just with Boolean algebra. So we're going to do three different methods of simplification. And so the bottom one, notice it's all NOR gates. So I converted it to a NOR gate circuit. The top one here is the simplified expression from this Boolean expression. But then I replaced the not B and not D with an OR gate, and that's equivalent. So when I operate it, I use the finger operation. So this is A, B, C, and D. The least significant bit is D. So this would be a 0, 0, 0, 1, right? And so I should have an output true for a 0 or a 2, right? So here's a 0, and the output is true on all the circuits. Or a 2, which is a 0, 0, 1, 0, the output is true. But for a 3, it should be off, right? And the 4 should be off. It shouldn't come on until we get to an 8. So there's a 4, and it's off. A 5 is off. A 6 is off. A 7, 0, 1, 1, 1 is off. Now an 8 will turn it on because we have an 8. So that's on, right? And a 9 will make it off. So 1, 0, 0, 1 is off, but a 1, 0, 1, 0 is on. So 8, and then a 1, 0, 1, 0 is 10. And 11 is 1, 0, 1, 1 is on, but a 12 will be off. And then a 13 is off. There's a 13. And a 14 is on, and a 15 is on. So our circuit, whoops, sorry, that's not a 15. Okay, there's a 14 is on, and a 15 is on. Okay, so it works on all the input combinations that we had, 0, 2, 8, 10, 11, 14, 15. And all three circuits are identical. So this is basically should be enough to get you started with Logisim. On here, I use those tunnels, which are over here under the wiring. So to use a tunnel, you just put it here. You put a label on it, whatever your label, and then you hook it up to some value. And you can, what I do is Command or Control D on Windows, and use the right arrow key, rotate it. So whatever's coming in here will be coming out on the other side. So if I hook up an input here, and hook up a wire here, and I hook up an output here, and because they have the same label, whatever I put in on one side will be coming out on the other side. So that's pretty basic on how to use tunnels. And on this circuit, we did not do anything with the wire splitters, but we will be very soon. So I'm going to demonstrate a wire splitter. I'm going to go back to the other circuit so we have a little room. Okay, so we don't need this for right now. I've already got the circuit done, so I'm going to delete all that. And I'm going to go here, and a couple things that we're going to do pretty soon is we're going to use our clock signal. It's going to be a little while, but we'll be using a clock signal, and we'll be using a counter. Oh wait, memory. Counter, here. This is a counter. So it counts in a 4-bit binary number. What I wanted to show you is the output on this signal, if I select it, the properties on the counter here is on the bottom left. it says data bit's 4, and the maximum value is 0xf. So f in hexadecimal is 1111 in binary, right? So it's got a 4-bit value on the output. Now look what happens. If I want to split those values out into their own bits, I can come here to a wire splitter. Now, if I use the right arrow or the left arrow, up arrow, I can rotate it around, right? Now, sometimes, I'm going to show you just to demonstrate. Let's say that's a 5-bit counter. So now it goes to 1F, which is 31 hex, right? But I wanted to demonstrate what happens. I've got 5 bits on the wire coming out of the counter and 4 bits on my wire splitter. So the wire turns orange, and it says here at the bottom, incompatible widths. So the reason for that is because they're incompatible. I've got 4 bits on this right side and 5 bits coming out of my counter. So what I could do is change my fan out on my wire splitter if I want 5 bits. So it's no longer incompatible, and I got bit 0 through 4. Another thing about this wire splitter is down here on the bottom, I have 0 on the top and 4 on the bottom. Frequently, I want it the other way around. So I want 4, like 3, 2, whoops, yeah, 2, 1. So frequently, I want it the other way. So I can reverse the order, and it puts 0 on the bottom and 4 on the top. So I'm going to go back to 4 bits here. And 4 bits. And I'm going to have an incompatible width again, right? So I'm going to make my counter 4 bits. Oh, this is something you could do if you wanted to. In fact, let's do this. So anyways, you saw about incompatible bit widths. You get an orange wire. And if I can find my other document, here it is. So here, yeah, it's back here. Here, find the header. There it is. Okay. Now maybe I want to see the numeric value for my input. So I can look at the number in decimal form, right? So I could take my A, B, C, and D here. I'll do that. And Command D, I'm going to duplicate those and put them over here if I have room. And I'm going to use a wire splitter and bring it over here. And now A is the most significant bit, but I got bit 0 on the top. So I'm going to reverse these to put bit 3, 2, 1, and 0. And the reason I wanted to do that is now bit 0, the least significant bit, is on the bottom, which is what I wanted. And that's not what I wanted. So I select the corner of the wire, right, and hit delete key. And that deletes that section from going both ways from the corner. So there is some wiring tricks you'll get used to. Now here I'm going to go to my display so we can see a numeric value for our input. So input output, hex digit display, and I'm going to stick that right here. Okay. So there's the value. So now when I change my input, I can see the values. So there's an 8, there's a 4, a 6, a 7. So we can see the values on our display by using a wire splitter with 4 bits input, and then it takes a 4-bit signal to the 7-segment hex, the hex digit display. So sometimes that helps to have a numeric value to show your 4-bit binary value input. Okay, so this is enough to get us started, I think. With the one more thing I want to show you real quick. I'm going to go to my file menu or project menu here and show you how to load the library. So the Logisim library, we have a 7400 lib-circ, and it should be, if you installed your Logisim according to the way I recommended, you have a Logisim folder in your documents folder, and in your Logisim folder you should have the 7400-lib.circ that I downloaded from the Logisim website, the cbirch.com website. So when I open that, notice on the right it added that library here on the bottom, on the left I mean. Okay, so now these are all the 7400 series ICs, like a 7408. That's a quad 2 input AND gate. So it's got 4 AND gates on it. So we're going to be using those soon. So I just wanted to show you how to use or load the library. And you can look up under datasheetcatalog.com, you can look up the pinout for that. Oh, this is a 7404. That's an inverter. Sorry, that's not a quad 2 bit. I thought I grabbed the 08. It's the 04. So that's a 7404 inverter. So this has 6 inverters in it on this chip. So anyways, so that's good enough for now. If you have any questions, feel free to email me, ask me in our class session tonight, or contact me with inbox on Canvas or however. Okay, thank you for watching the video and have a good day.